So today we are very fortunate to have Mr. Yi Cao visiting us. Mr. Cao is currently a fifth-year graduate student at Caltech, working with Professor Shirley Kukan on the intermediate Palomar transient factory, which is also called IPTF. Before he came to Caltech, he obtained a bachelor and master's degree at Tsinghua University in Beijing. As part of his thesis, he conducted several rapid cadence transient search experiments in IPTF, focusing on observations of young supernovae. Today, he'll talk to us about the IPTF experiments and some highlighted results.
Thank you for the introduction. So today I'm going to talk about observing young supernovae, and observation of the young supernova will tell us a lot about its progenitor system. And in order to search for young supernovae and characterize supernovae, we have to find it fast, and then we have to do our follow-up observations very rapidly. That's why I give my title, give my talk a title, Fast and Furious. It has nothing to do with the movie, by the way. So the question is quite old. So supernova has been discovered since 1,000 years ago by Chinese. But the real modern supernova search started back in the 30s by Fritz Zwicky at Caltech. And since then, we discovered almost more than 10,000 supernovae. Especially after the 1990s, when different large supernova search programs like Lick Observatory's Supernova Search, PTF Pan-STAR, and SDSS, we have found so many supernova, and the cost for that is we have spent hundreds of thousands of tens of times to observe this supernova. But we still don't quite understand what kind of stars explode supernova. Supernova are rare cases, rare events. So we find most of supernova in very distant galaxies. But for stars, on the other hand, even with HST today, we only find stars at very nearby galaxies. And for example, for the brightest stars, we can find them up to about 20 megaparsec. So roughly, we know that for type 1a supernova, they're exploding white dwarfs. And for core-collapsed supernova, they are massive star explosions. But we don't know how this matter exactly is. And so one of the long-lasting questions in supernova world is to look for the progenitor systems of supernova and characterize their nature. The most traditional way to do that is through this fortuitous pre-supernova image. The idea is quite simple. You find a supernova in a nearby galaxy, then you go back to your archive to look for something at the location of the supernova. If you find something, and then you claim that that's a supernova progenitor candidate, and after the supernova goes fade away, so you take another image and find that the candidate disappeared. Then you say that I find a supernova progenitor. And then you can put it onto the HR diagram to constrain the properties of the supernova progenitor. And this has been done for many, many cases. And from this method, we have identified more than a dozen of progenitors for type 2 supernova. But for about a dozen cases of type 1bc supernova, all we have is end up with upper limits at around this level. That may be because type 1bc supernova have a faint progenitor. And also for type 1a supernova, even with the type 1a supernova of only 6 megaparsec away, we haven't seen anything at the location of the supernova before the supernova, in the image before the supernova. So we put a very strong constraints on the HR diagram for the progenitor systems, like indicated in the yellow region here. But we still don't know what the progenitors are. So with that being said, this method is very useful for type 2 supernova, but it's not efficient to look for progenitors and constrain the nature of type 1bc supernova. So we need new method to do that. One way to do that is through the supernova shock cooling. So imagine that supernova starts from the supernova shock breakout. After the shock breakout, you just have a blob of gas or material with high temperature and high velocity. They expand freely and in the same time cools down adiabatically. So the physics is relatively simple at this moment. So if you and this at this moment the light curve is shown in the blue part here. So if we observe the supernova at this very early time, and then we assume some structure or information of the supernova supernova ejector, then we can work the physics back to at least infer the size of the progenitor system. And this has been done in a few cases, and it has demonstrated to be a very powerful method. So we want to do it systematically with a large number of supernovae. And another interesting aspect for supernova is imagine that when the supernova explodes, you still have the supernova explodes from a binary system. So the companion star may exist when the supernova explodes. So it's inevitable for the supernova ejector to hit the companion star. And according to a rough model by Dan Kaysen, and this collision initially produced a very strong X-ray flash on timescales of tens of minutes. And then this collision energy just diffused out and thermalized to produce a strong UV diffusive emission on timescales of a few days. With the current X-ray instrument, it's really hard for us to catch this X-ray flash on timescale of tens of minutes. But UV emission lasts for a few days, so it's feasible for us to observe this UV emission. And if we observe this UV emission, that will be a very strong evidence for the existence of companion star. But also, you should notice that this emission is actually orientation dependent. If you observe from the top, like this guy here, you will see that both the X-ray flash and the UV emission will be propagated into your telescope. But if you are unlucky to observe it from the other side, all the emissions will be shaded by the optically thick supernova ejector, and you won't see anything. And that means that if we really want to find this supernova companion interaction signature, we need to observe a certain number of supernova and for this supernova companion interaction signature. With these two motivations, we started a new experiment called intermediate Palmer transient factory. And this plot just gives you an overview of our experiment. So we use the 48-inch telescope to look at about 1,000 square degrees every night. And each field is observed twice, separated by about 30 to 45 minutes. And that enables us to find the young supernova. So in terms of limiting magnitude, we go down to about 20.5 in G band, in R band, and the 21st magnitude in G band. So we just put, we also developed a fast turnaround pipeline at LBL, which essentially does regular image processing and image subtraction in order to find the young supernova candidates. And this pipeline can reliably deliver us supernova candidates within 10 to 15 minutes of images being taken. And with that, we also use machine learning classifiers to get rid of most of the artifacts. And that ends up to about 200 to 300 candidates for human scanning every night. And we also built a scanning group in Europe to look at these images every 10 to 15 minutes. The reason for that is when we observe in the US, it's our sleeping time. So we are all sleeping, but it's daytime in Europe. So they could work and they can look at the images in every 10 to 15 minutes. Once they find something very interesting, they alert us, and through message, text message, emails, even phone calls to wake people up in the US, then we can trigger TO observations at the 200-inch telescope, at the Keck telescope, and as well as Gemini telescope for follow-up. And this actually happens about once a week. And then we also trigger other telescopes like SWIFT and HST for UV observations, and we also use radio for fast for observations of young supernova. We also have agreement with LCOGT to do a continuous follow-up. This histogram gives you some idea about the performance of our experiment. So we get all the type 1, all the supernova with registration point 1. And on the left-hand side, what I'm showing you here is a histogram of the time difference between the last non-detection of a supernova and its first detection. It essentially tells you how young the supernova is. And you can see that between 0 and 5 days, we find a lot of young supernova. And on the right-hand side, I'm showing you the time lag between our discovery and our first spectroscopy follow-up. As you can see, for more than 80 supernova in the last 2 years, we could get this first spectral within 24 hours of discovery. So this actually enables us to do a lot of interesting science. So next, I'm going to highlight some results from my own work. First, let's talk about type 1a supernova. Let's come back to this supernova companion interaction. As we know that type 1a supernova are used extensively for cosmology, and but the origin of the type 1a supernova is still mysterious. There are two competing scenarios. One is the so-called single degenerate channel, where you have a white dwarf accreting mass from companion star, and the white dwarf mass of the white dwarf increases until it approaches the Chandra mass limit, and then the supernova goes off. And in that scenario, you would expect to see this supernova companion interaction signature. And in the other scenario, which is called the double degenerate channel, two white dwarfs spiral in and merge, or even collide with each other to produce this type 1a supernova. But in that scenario, you won't see the supernova companion interaction because there's no companion at all after the supernova explodes. So if we see this supernova companion interaction signature from a type 1a supernova, that would be a very strong evidence to support this single degenerate channel. But back in 2012, the reality is not many type 1a supernova were observed in the UV, probably because some technical difficulty. So this is a compilation of Swift light curves on the 6 Swift UV-OT band for all type 1a supernova back in 2012. And as you can see, not many supernova were observed at early time. If you focus on the first, let's say, 5 days, there's only less than a handful of supernova observed with Swift. And it's also not surprising that we haven't found that supernova companion interaction signature, because there's a strong geometry dependent. You only expect to see them in about a few percent to 10% of the events. So we did this practice. We did trigger Swift observations for about 9 young type 1a supernova in our past 2 years. We only triggered Swift for things within 100 megaparsec. And luckily, we found something super interesting. This is a type 1a supernova, IPT of 1480G. As you can see, the red shows the light curve of this guy. And unlike any other supernova, which is shown in red, it shows a strong declining emission in all the 3 UV filters. And in the U band and B band, you just see a flattening here and flattening here. And in the V band, in the first 2 epochs, we just don't detect the supernova at all. This actually tells us this early component in the light curve is mainly concentrated in the UV wavelengths, or even in shorter wavelengths. And it lasted only for several days after the supernova explodes. The luminosity is about 3 times 10 to the 41 ergs per second. So this is actually quite consistent with what we expected from supernova companion interaction. So we go ahead to use the scaling relation from Dan Kaysen and find that our data can be well explained by a supernova interaction from a binary system with a separation between 17 to 90 solar radii. There's a modal degeneracy here, but qualitatively speaking, our observation is consistent with supernova companion interaction. So that strongly supports the existence of companion star. And we also have SED during the supernova companion interaction. As you can see, there's R-band data and optical spectrum and Swift data here, and the two dashed lines as the black body spectrum derived from the models. And except for these points, the models are roughly consistent with the observation. For these points, we were thinking that there may be some line emissions that would tell us a lot about the supernova companion interaction physics. So what we did is in the next HST cycle, we are awarded 3 orbits to get a UV spectrum of a similar events. We can find another one in the next year. And so the next job is of course to look to see what kind of type 1a supernova this is. I'm showing the spectrum sequence and light curve here. So in the spectrum sequence, during the UV pulse, you just see a blue continuum without seeing any characteristic features of type 1a supernova. And that is probably because most of the emissions at that time is dominated by the supernova companion interaction. But a week later, or just 10 days before the maximum, you start to see the silicon features here, the sulfur W features here, which are characteristic features for type 1a supernova. And near max and a week after max, we actually find a good match between this supernova and the non-type 1a supernova 2002 ES. But note that 2002 ES is not a normal type 1a supernova that people use for cosmology. This is a low velocity type 1a supernova. It has a low expansion velocity of about 8,000 km per second compared to more than 10,000 km per second for type 1a supernova near max. And it also has a fainter, has a lower peak luminosity. And for example, for 4080G, it's about 1 magnitude fainter than a normal type 1a supernova. It has a wider light curve. So this 4080G is quite consistent with something like 2002 ES. And some people may argue here that this is not a type 1a supernova. This is just the shock breakout of a cold collapse supernova. But my argument for that is you don't always see this sulfur 2 lines and sulfur 2 lines, especially the intermediate mass lines from type cold collapse supernova. And more importantly, if you look at the host galaxy of this event, it's a completely dead galaxy without seeing any star forming activities. So we are thinking this is probably a type 1a supernova. After we published this paper, we also got a nebula spectrum of this supernova. As usual, from type 1a supernova, you see all these iron 2 lines and calcium 2 lines. But surprisingly, we find the oxygen 1 lines, nebula lines. This is the second case that shows the oxygen 1 lines, nebula oxygen 1 lines from a type 1a supernova. And the velocity of this oxygen 1 line is about a couple of thousand km per second. So we don't have a good interpretation for that, but the two scenarios to interpret that is, the first one is, this is some unburned material near the center of the supernova. So at very late time, you start to see this unburned oxygen 1 emission. Or this might be some emission from the stripped material from the companion star. We don't know. This need more work here. Okay, this is for type 1a supernova. Then we also did some did some work for young type 1b supernova. As I told you that for about a dozen cases of nearby type 1b 1bc supernova, we haven't seen any progenitor system. But luckily, back in 2013, from this type 1b supernova 13BVN, we find a progenitor candidate. Here, I'm showing you a beautiful HST image of the supernova host galaxy before the supernova goes off. And this is just the zoom in of this host galaxy. And this is 3 HST band, the B band, V band, and I band. And here is the AO image of the supernova. And if you register this image with all this with the HST image, you do find a point source at the location of the supernova about 5 sigma. So if this is the first supernova progenitor candidates for type 1bc supernova, if we put that onto the HR diagram, it's consistent with Wolf-Rayet star. And of course, because in the HR diagram, you can also fit other evolutionary track like some binary system evolution. And we also use an early light curve to constrain the size of the progenitor. So we have 2 non-detections before the discovery and 2 nice observations after since the discovery. And we don't know how to decompose the shock cooling phase of the supernova from the supernova light curve powered by the Nico 56. But we know that the shock cooling light curve cannot exceed the non-detections and the detections. So we tried a model developed by Tony Pyro for the post-shock breakout cooling. And we find that depending on that model, the size of the progenitor cannot exceed 4 solar radii. So that the number of 4 solar radii actually depends on the model, but qualitatively speaking, this one, the progenitor of this one is not a giant star. It's not a supergiant. It has to be something similar to the size of our sun. We also get radio observations for this supernova, and the radio observation comes from the synchrotron emission of the circumstantial medium shocked by the supernova shock, and it's just a standard synchrotron self-absorption model. And if we assume that the progenitor has a mass loss, has a stellar wind of about 1,000 kilometers per second, the mass loss rate for this progenitor has to be about 10 to the minus 5 solar mass per year. So HST will revisit this supernova site again sometime this year and next year to see if the candidate here actually disappeared or not. If it's disappeared, it will be the first confirmed type 1b supernova progenitor. And I also work on other things like type 1a supernova between Noma and Chandra events. And we also find a very fast and faint supernova, which may be associated with the fallback formation of black hole. We also find some high ionization lines, which actually tells you the chemical abundance of the supernova progenitor. So if you are interested in any of this topic, just come talk to me. For the last couple of minutes, I'm going to talk about the future. So in future, we will have a monster camera called a Zwicky Transient Facility, and it will have a field of view of 47 square degrees, and that will actually enable us to increase our survey speed by a factor of at least 10. With that being said, right now we are discovering about 1 young supernova per week, and with ZTF we expect to discover about 1 young supernova per night, and that will actually hugely increase the number of young supernova and provide more information about their progenitor system. And we also, our experience about doing this faster response to young supernova will be very suitable to look for the EM counterparts of advanced LIGO triggers, and we are actually putting some effort on that. So here's my summary, and I'm happy to take questions.
It's very impressive results. Yeah.
The type 1 is supernova example that you showed. Can you comment on what kind of a companion is it?
Well, okay. So the model, depending on the model, we find that the separation of the binary system might be between 17 or 90 solar radii. And if we assume this is a Rauschlove fitting binary, and if we assume the mass ratio is not crazy, like between a few to several, then you would expect that the size of companion will be 10 or 20 solar radii. So it could be just some subgiant star or even big main sequence star.
I guess what I'm coming to is the companion should have wind. Do you have any radio observations?
Well, that's a little bit unfortunate. We triggered radio, but the radio didn't start observing it until a week after we discovered it, so it might be too late.
In the example that you showed, I think it's one BVN.
Yeah.
So you're saying that this is a Wolf-Rayet progenitor.
I'm not saying that's Wolf-Rayet star.
But it could be.
It could be, yeah.
But do you have any evidence of lack of binarity?
I'm sorry?
Lack of binarity of the...
Oh, no, we don't have. Well, actually, if you look at the light curve of this guy, so just for light curve of this guy, it may suggest that the ejected mass of the supernova is only 3 solar mass also. But the observation of Wolf-Rayet stars tells us the Wolf-Rayet stars have a mass between 10 to 15 solar mass. So there's still a big gap in the mass. So some group claims that the progenitor might be a binary system instead of Wolf-Rayet star. So that's still an open question. Yes, Alicia.
So how well do you believe in the models that you're comparing the data to?
In what model?
So you're comparing your models to the shock breakout models
Mm-hmm.
for thermonuclear and for pulsar supernova. How much trust do you have in the fact that they are correct?
The most uncertain part for the model is actually the structure of the density and velocity structure at the very outer part of the progenitor. So for most cases, unless it's very peculiar, I think most of the models are qualitatively consistent.
But you just shown us two unusual suspects.
For certain BVN, it's quite normal type 1b supernova. But for the 1A, we are not we are comparing to the supernova companion interaction model, and Dan Kaysen's model is the only one that is available at this moment.
Right.
But I agree. So we definitely need a more detailed model to actually do like radiative transfer for the supernova companion interaction, and I think Dan is planning to do that.
Great.
If there's no other questions for E, then thank you for this.
Thank you.
Our next talk is given by our Dr. Malgosia Sobolewska. Back to 2002, Malgosia was a SAO pre-doc working with Anita Shimichinoviska. She got her PhD in 2006 from the Copernicus Astronomical Center in Poland. Dr. Sobolewska did postdoc research in Durham University in UK and University of Crete. She joined CFA as a postdoc in 2009, continued to work with Anita. Her work mainly on the AGN time variability in X-ray and gamma ray bands. She has also been working as a part of the European consortium. In January 2016, she's starting a tenure track position in the Copernicus Astronomical Center. Today, she's going to talk to us about X-ray properties of the youngest radio sources and their environment.
Thank you for the introduction. So indeed, I'm going to present our results of the latest X-ray Chandra program on the young radio sources. And this work has been done as a part of a group led by Aneta, who was the PI of our Chandra project. So even though I will talk about young radio sources, I wanted to start by showing this perhaps the best known radio galaxy and the best studied one. It is a Cygnus A, and the image comes from the Chandra photo album. In this image, blue color corresponds to the X-ray emission, and red color is tracing the radio emission that is due to a powerful jet launched from the center of the galaxy, and it extends way beyond the host galaxy, forming those gigantic radio lobes and the hotspots. So the hotspots are the locations of the jet colliding with the surrounding medium. And you can see that the separation of those hotspots here is of the order of hundreds of thousands of the light years. So I am not going to talk about this type of sources. Instead, I will talk about compact symmetric radio sources. And those sources were nicknamed baby Cygnus A sources like about 2 decades ago. So compact symmetric objects, they are a subclass of the so-called gigahertz peaked sources. The main characteristics are a turnover radio frequency at about 1 gigahertz and a linear size in radio that is very compact, below 1 kiloparsec. So the main characteristic is a symmetric radio morphology, and you can see it here on this example. This morphology is dominated by a two-sided structure with mini lobes and hotspots. And because of this symmetricity, we are quite sure that we are seeing those sources perpendicular to the jet axis. So the age of those of the CSO sources can be found based on the linear radio size and the hotspot advanced velocity. And this is a principle of so-called kinematic age measurements. And in the case of the source I am presenting, Park 1718, this age has been estimated to about 100 years. So this is a youngest and as well the nearest CSO source known to date. So we aimed at studies of the CSO sources with measured kinematic age, and also we wanted to study the sources that are nearby, so within a redshift of 1. And because kinematic age measurements are quite difficult, they require multi-epoch radio monitoring. There are only 16 sources known with kinematic age and redshift less than 1. And each of those sources here is represented with a square. So before our project, there were only 7 sources observed with XMM, 2 sources observed with BeppoSAX, and there was 1 archival Chandra observation. So we revisited the BeppoSAX sources, and we also looked at the most luminous XMM sources, and then we observed 6 of the sources for the first time in X-rays. So this will be our Chandra sample, our CSO sample that I will talk about. Here I am showing a graph that is presenting the ages of our sources, and you can see that the ages range from about 100 to about 3000, with about half of the sources in our sample that are younger than 500 years. So before I present the results, I wanted to quickly talk about motivation for this work, and I will highlight 2 main things. One of them clearly is the evolution of the radio sources. I am presenting here 2 images of the evolved radio galaxies that are classified into 2 types, FR1 and FR2, according to the well-known classification. FR1 sources are dominated by bright radio cores and inner jets. They are less luminous in radio, while FR2 sources are dominated by the hotspots and extended radio lobes, and they are more powerful in the radio band. It seems from the recent studies that there is an emerging FR0 class as well among the radio sources, They show properties similar to the FR1 galaxies, but they do not have extended lobe emission. So the main question people are asking is, what happens to the young radio source? Young radio source has all those possible paths for the future to choose from. It may evolve to FR0, FR1, FR2, or it may never develop a large-scale structure, and it may fade before that stage. I'm showing here a plot describing the radio luminosity at 1.4 gigahertz as a function of a linear size of the radio source. And here the evolved radio galaxies are on the right-hand side of the plot, and the GPS sources, which is the parent population of the compact symmetric sources that we are studying, are on the left-hand side of the source. The sources, radio galaxies at the intermediate stages of the evolution, are here in the middle. And we would like to know how the evolutionary paths proceed while the sources are aging. Whether the powerful GPS sources are evolving into the powerful galaxies, or whether there are some different possible evolutionary paths possible, whether those are intrinsic physical properties of the nucleus that is powering the radio sources that is determining the evolution, or maybe this is more due to the environment in which the galaxies are expanding. And the second important motivation is the well-known interaction between jets and the interstellar medium. I am showing here an example of, again, an evolved galaxy from the work our group has done a few years ago. This is an X-ray image, and you can see here signatures of a complex interaction between jet-driven radio outflows and the environment of the host. Those circles here and at the bottom, this is an X-ray emission that is coinciding very well with the radio hotspots. There is also a strong emission in the center of the galaxy. The radio jet is oriented along this direction, but the X-ray emission is extending much beyond the radio source, and there are multiple regions marked here with the green shapes that are that give clues that interstellar medium is heated by weak shocks driven by the expanding radio source. So quickly, I wanted to review now several ideas, theoretical ideas that are invoked to characterize the size of the CSO X-ray emission, and one of them is, of course, the active nucleus. In this scenario, the X-rays originated due to inverse Compton scattering of accretion disk photons, presented here in blue, of the electrons in a hot X-ray corona. Some of this emission may be absorbed by a molecular torus. X-ray may also be due to thermal emission of the interstellar medium, heated due to the interactions with the expanding jet, or they may originate in the radial lobes. And in this scenario, here the radial lobes are presented with gray shapes here. And in this scenario, X-rays originate through inverse Compton scattering of local photon fields. The works of our collaborators indicated that dominant photon fields for radial lobe scenario come from the UV disk, or they are infrared and they come from the torus. So in terms of observations, please note that we are investigating Chandra regions that are about 1.5 arc seconds, and this corresponds to a physical size between 0.4 and 10 kiloparsecs, while the radio linear sizes of our sources range between 2 and 100 something parsecs. So basically, the radio source is unresolved in our images, and the X-ray emission may contain several components which we want to study through spectral analysis. So, for example, we will be looking for an extended X-ray emission. We will want to determine what are the photon indices of our spectra. We will look for intrinsic X-ray absorption and evidence for features such as iron emission lines, for example, that would tell us something about reflection or scattering properties of the sources. So in practice, we are fitting absorbed power law models or thermal plasma models or complex models, being a combination of the two. So now I am going to present the main results of our study, and I will talk about 4 most important results. First of all, indeed, we do detect extended X-ray emission in the source that I was showing at the very beginning. This is the closest and the youngest source in our sample. In this plot, I'm showing the surface brightness profile, and the yellow horizontal line corresponds here to the constant background. Blue is the Chandra PSF, and the red curve is the total model, and clearly we see residuals between 2 and 6 arc-second scale, which can be accounted for by adding an additional component. So it's quite clear that there is an extended emission in this source. The other result that I want to talk about is the detection of an emission line in the harder Chandra band. This emission line, if modeled with a simple Gaussian, it has energy in the rest frame of 6.6 kiloelectronvolts, and we associate this line with the ionized helium-like iron species of 25. The modeling that is presented here is very simple. It's a power law or a power law with a Gaussian line, but then to investigate what is the origin of the emission line, we tried also more complex models. So in one case, we modeled the soft part of the spectrum with a scattered nuclear emission, and then the iron line would be related to that scattered emission. We require that 13% of the nuclear emission is scattered, but some sort of ionized matter, and the iron line has a very large equivalent width. And in the second case, we assume that the iron line and the soft part of the emission is due to the thermal plasma. We get temperature of around 5 keV in such a scenario. The third result I wanted to highlight is the discovery of a possible Compton-thick CSO candidate in our sample. So I wanted to briefly remind you what are Compton-thick AGN. Those are sources in which the direct emission is obscured by a very high column density of the order of 10 to the 24 per centimeter square, and the emission is observed only in reflection. So in the case of no obscuration, the spectrum in the Chandra band would be power law-like with an iron line. But once the direct emission is obscured with higher and higher columns, the apparent photon index of the spectrum steepens to very hard values, and the iron line appears to be more and more prominent. So in this case of the source, we detect a photon index of 0.8. We do not see, however, the evidence for the iron line. And this may be either due to the fact that the iron is not present in the spectrum, which would not fit the Compton-thick scenario, or simply there may be not enough signal in the soft part of the spectrum to detect the line. So up to date, there have been several Compton-thick CSO sources reported. The best known is the source observed with XMM Newton in 2004. Our source that is a candidate of a Compton-thick CSOs, and there were also reports on 2 other sources observed with XMM and 2 sources observed with Beppo-Sachs. However, of these 4 sources, 3 are not Compton-thick in our data. We do not see evidence for a strong obscuration, and 1 was not observed. So this is quite interesting, because if all those 6 sources that have been proposed to be Compton-thick are really Compton-thick, then it would mean that there is about 40% of Compton-thick CSOs in our sample, which compared to the Compton-thick sample in nearby AGN, which ranges between 20 and 40, seems a little bit high. So this is an interesting question to resolve in future. The last result. Okay. So I wanted to talk about one of the sources that was Compton-thick in the XMM observation. However, we do not see the evidence for this sort of nature in our data. So in XMM Newton, it was detected with a very hard photon index, and the equivalent width of the iron line was about half a keV. Instead, in our data, first of all, we see a much softer, still high, but much softer photon index that can be easily accounted for by a standard nuclear emission. And also, we resolve a secondary source that was within the extraction region of XMM Newton. However, this source is very faint, and we do not think that it could dominate the XMM Newton data. So those are very particular variability properties, given especially that in our observation, the source was about 1 order of magnitude dimmer. So one of the interpretation is that this source may be a transitional source that switches the states between Compton thick and Compton thin. But in such a case, we would expect that the flux and luminosity in the Compton thin case, which is our Chandra observation, would be higher. And this is not the case. So a very interesting source as well. Finally, I wanted to summarize our findings on the intrinsic X-ray absorption. So in this graph, I am plotting together all the sources that were so far observed by Chandra XMM or BepPo-Sachs. Intrinsic column density is on the y-axis in the units of 10 to the 22, and the age of the sources is on the x-axis. The open symbols indicate that there were too few photons collected, and the photon index was fixed at a typical value of 1.7 to get an estimate of the intrinsic absorption. The vertical lines here connect points for observations with different satellites, so Chandra and BepPo-Sachs or XMM Newton, or observations for sources that we modeled in two different ways. So this upper red square here is for the Compton thick case, and this square is for the Compton thin case. And one apparent thing is that perhaps there is a dichotomy seen between Compton thick and unobscured sources, which has to be confirmed or rejected. So on the right-hand side here, I am showing the unabsorbed X-ray luminosities in 2 to 10 keV band, and it can be seen that our sources cover about 3 ranges of magnitude in the luminosity. Now I wanted to talk about our results on intrinsic X-ray absorption in the context of multi-wave band studies. I am showing here a cartoon of different possible geometries that relate the location of the radio sources in blue and X-rays in pink. And the clouds here indicate the radio and X-ray absorbers. From the works of Luisa Storero, that is our collaborator, it follows that absorption in X-rays and in radio is strongly correlated. And this implies that X-ray and radio absorbers are cospatial. So because of that result, we can exclude the scenario in which absorption in X-rays and in radio is due to clouds that are separated from each other. So this would mean that both the X-ray and radio source are enshrouded with some sort of material that is obscuring the radiation in a correlated way. So cospatiality of X-ray and radio absorber doesn't mean that the sites of X-ray and radio emission are also coinciding. Still, the X-ray emission may be either only from the nucleus or from nucleus and the radial lobes. Okay, so I wanted now to summarize our findings. First of all, it has to be noted that we have a really high CSO detection rate, even with the snapshot observations. Most of our observations were only 5 kiloseconds. And our Chandra program revealed that CSOs form a heterogeneous population, and they are expanding into a diverse environment. The most important findings is a complex surface brightness profile in the nearest source in our sample. We argue in favor of nuclear origin of X-rays in the source in which we detected an ionized iron line, although thermal ISM emission cannot be excluded. We also found a possible Compton-thick CSO candidate, but again, it has to be stressed that non-thermal lobe emission cannot be excluded. Such hard photon indices can be obtained with a little bit extreme, but still plausible electron distributions. And we find some indications that there might be a dichotomy of Compton-thick versus unobscured CSOs in our sample. So clearly we need deeper observation, better observation, and probably broadband X-ray observation to discriminate between different models, to study CSO time variability, and constrain the Compton-thick CSO fraction. Thank you.
Any questions for Malgosia?
Yeah, I didn't get the final statistics. Is it 2 of 16 are Compton thick?
So our sample are CSOs at redshift below 1 and with kinematic age measurement. There are 16 sources, and there have been 6 sources proposed in the literature to be Compton thick in at least one observation. So it's 6 of 16.
At some time.
Yeah.
But they're not. I mean, at least some of those were not always. Were also seen to be not Compton thick at a different time.
Yes, it's true. It's true. So either they switch the states, or either there is a very complex dynamics going on in this on the small parsec scales with clouds that cover and uncover the view. Yeah.
But there's no doubt about the observations that they really did switch.
This actually. So okay, let me go back to one of the. I wanted to show maybe okay, this plot. So here, for example, there are 2 sources that were reported to be Compton thick in the Beppo-Sachs observations that look at the regions of about 2 arc minutes, right? Okay. So we aimed Chandra at those 2 sources. We studied 1.5 arc second region, and we do not see that they are Compton thick. They are not Compton thick in our observations. So it might be that the Beppo-Sachs just aimed at a much larger region, and the emission for some reason was not coming directly from the sources, right? And in the case of this source, this is the source for which we see the counterpart and a very unusual flux variability. So again, the situation may be very complex there.
So this source that you say that that was Compton thick, and now you don't see the Compton thick, and you see this variability.
Mm-hmm.
Did you go back and look at the XMM data again?
We did.
And?
So those numbers match. They are confirmed.
So those are your numbers. So
those are numbers. Yes. So this.
Okay.
Yeah.
Okay.
So Aneta participated in this project, and also Matteo Guainazzi, who is.
Okay.
Yeah.
So this is a true variability.
Yes. It's real.
Do you have any planned follow-ups with restart?
We were considering that. Yes. Maybe we should talk about this, because this would be really good to have the.
Be a good next step.
Mm-hmm.
So are those not too painful?
Yeah.
Because this was one of
This was one of our concerns, but definitely we should discuss that.
10 to the 114, you maybe need 1 to few seconds.
yeah, that's what that's
But why not? We are open to.
because they are of that order and not
Mm-hmm.
But you could apply for XMM and NuStar to have.
Yes, the deadline is tomorrow.
Well, but the point is that your sources are variable. So
Yes, yes.
How do you do it if it's again saving variability?
Yes, we have to control for the second source for sure. So looking at this again with XMM only.
But you know that there is a source there.
Yeah.
yeah, this one is very faint. There was 40 seconds of Chandra acceleration on this, and you get just to
Yes, so this is one of our deeper observations.
we based our predictions on excellent counts, and we just went down. So.
So the flux here is, you can see 1 order of magnitude lower. Yeah.
There's no other questions. Let's let Malgosia keep writing George Excel